So let's go ahead and get started. If you open the slideshow at the top, you'll see this is, of course, the idea of entropy is our topic today. On the introductory slides in each of these shows, I have links to all the bites of physics, to a few nibbles of physics that I've done that I had a better idea for at one point. That isn't a very big collection. But there's some there. And they're just in general to all of my public documents, which are surprisingly heavily slanted towards flat earth rebuttals these days. Some of you know I spend way too much time in the flat earth rooms. And there is a certain fascination both with the psychology of flat earth, but also with the fact that they bring up questions that you can actually address, both theoretically and observationally. And I've done a lot of that in a lot of the materials that I've presented. So if anybody's interested, you can always peruse the documents in there. So let's get started with slide 2. Statistical mechanics versus classical thermodynamics. Statistical mechanics is a more recent version of an older study in thermodynamics, which began well before we had any clear indication that atoms existed. Classical thermodynamics is about concepts like pressure and temperature, volume, etc. All things that can at least conceivably exist if all matter is kind of infinitely divisible, continuous, if matter is just blobby stuff that doesn't come in the form of atoms. It's hard for us to conceive of that these days, but there was a raging debate for a very long time about that. And classical thermodynamics doesn't depend on the existence of atoms. You can talk about the behavior, the thermodynamic behavior of things without knowing that they're made of little chunks. Statistical mechanics, it's good just to read what Google AI, I Googled this phrase, statistical mechanics versus classical thermodynamics, and Google AI came back with something that I thought was, for a change, pretty good. This one sentence I think is good. While both study the behavior of systems in terms of heat and energy, thermodynamics focuses on macroscopic properties like temperature and pressure using empirical, and I emphasize that myself, empirical laws. So we make these observations, we come up with laws describing the relationships between them, while statistical mechanics uses the microscopic properties of individual particles, aka atoms perhaps, to explain and derive the macroscopic thermodynamic behavior of a system. So the empirical laws that were known for a very long time before we were certain that there were atoms are now actually derived from statistical mechanics ideas, just the idea that macroscopic objects are made of incomprehensibly large numbers of little pieces, and it's the statistical behavior of those pieces that actually determines and from which we can derive the laws of thermodynamics. So as I say then going on, for instance, in statistical mechanics, we find that temperature generally reflects something like the average kinetic energy of the particles, of the atoms or the particles in a system. And pressure is the result of particle collisions. All such thermodynamic quantities are sharply defined and free of fluctuations. And I say that, let me just focus on that for a second. As soon as you realize that matter is made of little particles, and you start trying to say that temperature has to do with the kinetic energy of particles and pressure is the result of collisions, then you might think that those things are kind of jerky and fluctuating. Pressure should be all these atoms banging up against something. Well, you'd feel all those little bangs, and sometimes there'd be kind of more bangs per unit time than others, and you'd have more pressure. Kinetic energy of particles can fluctuate due to collisions. Maybe some have more energy than others. You might think that all those things things would lead to not very well-defined quantities. But the fact is that they are very sharply defined and entirely free of fluctuations in time and space for systems that consist of a large, really technically infinite, effectively infinite number of particles. And two are in thermal equilibrium. So thermal equilibrium is the only for systems that are in thermal equilibrium can you talk about the pressure. For instance, a gas in a box. If that gas has not come to thermal equilibrium, then it doesn't have a pressure. It will be maybe sloshing back and forth. You can imagine a gas in a box that you've put in, that you've blown in, and maybe it sloshes back and forth a couple of times before it kind of settles down. And it may not have a temperature because maybe parts of the gas are kind of moving faster than other parts, et cetera. But the first law, the zeroth law of thermodynamics, effectively, has to do with the idea that things will come to thermal equilibrium, that things will come to a point where these quantities like temperature and pressure are well defined. The kinds of systems we imagine really are systems with numbers of particles that are typically measured in at least substantial fractions of moles. A mole of particles, you may know, is Avogadro's number, which is 6 times 10 to the 23rd. What is that? That's 600 million thousand particles. I have to kind of add up all the zeros there. Or 600,000 billion particles, I guess is what that is. So that's a very large number of, and when you start talking about the statistics of a very large number of particles like that, the numbers get even larger. The kinds of numbers that you have to deal with in statistical mechanics are things like 10 to the 23rd, those kinds of numbers. A 1 with 10 to the 23rd zeros after it, which is kind of a hard thing to imagine as well. But we come up with ways of dealing with that. So let's move on. Let's talk about some really elementary statistical ideas. Actually, let me just stop for a second, see if anybody has any thoughts. I don't know that I've said anything that is very puzzling yet. But
I just want to ask if we're going to define temperature and pressure and all these quantities using are you going to go there, or is it not today?
Yeah, we're not going to do that today, but we will certainly get to I shouldn't say certainly. If this series does go on for another week or two, we'll certainly talk about temperature, and we'll certainly talk about pressure too. I think in fact I may have already done that in a previous bite of physics, but we'll definitely revisit that as well. But not today. Not today. Just really pretty elementary statistical ideas today, and really getting a little better idea of entropy. I hope maybe a better idea of entropy than most people have. Most people carry around what they think is a good idea of entropy, but really isn't, because it's not on a very solid mathematical basis. I'm going to give you a little more solid mathematical basis for understanding it. So we start by just talking about rolling dice. And in particular, if I start by rolling one die, there are only 6 possible outcomes. And if it's a fair die, then each of those 6 possible outcomes has an equal probability. You roll the die, you either get a 1, 2, 3, 4, 5, or 6 with equal probabilities. And that's shown in the graph on page 3, the upper graph at the right. There's an actual I can't remember, if you go to the link at the bottom of the page, you'll see more about the 2 graphs that I put on this page. It may have been simulated rolls. They may have written a computer program to simulate the rolls of 1,200 dice, or they may have actually done that, but I doubt it. I suspect they probably simulated it. So there is a simulated version of rolling a die 1,200 times. You see that you don't get the same number of ones as twos, as threes, fours, fives, and sixes, but at least you get results that are in line with the expected. That with 1,200 rolls, you'd get 200 times, you'd get one, 200 times, you get two, and so on. So that's it's a really important thing to look at those deviations. The fact is that there's deviations there by as much as 10 or maybe even 20. Looks like between 10 and 20 is kind of the typical deviation from the expected number of 200. Those are pretty big deviations. Still, there's no question that the basic data agrees within some expected fluctuation with the theory that they should all be the same.
Whatever they did, they hated even numbers. That's what I can see.
That's right. You do notice that. Isn't that interesting? Maybe it was a loaded die of some kind, a loaded simulated die of some kind. I hadn't noticed that myself. Actually, the fact that it does that almost makes it look like it's fake. It's like they just simply drew a thing that had some up and some down, and they said, "Okay, let's have one up."
And then they copied it 3 times, like 1 and 2, and then copy paste.
Yeah, so it could have been. Nevertheless, whether it's simulated, whether it's real, actually throwing die, or whether they just drew it and said it could come out like this, you really can't tell, because your intuition should tell you that something like that could probably happen. We could actually analyze the statistics using advanced statistics methods and see how unlikely those fluctuations are. It might turn out that they're very unlikely, but I doubt it. They look pretty reasonable. My intuition tells me that. When we roll 2 dice, and this is the reason we do roll 2 dice, is to get outcomes that have different probabilities, right? When you play craps, it's important that 7 is an easier number to get than snake eyes or boxcars. That's kind of rolled into the game. Not roulette, what am I saying? Craps, right? When you're playing craps, that's kind of rolled into the game. And as I say there's one way of getting a 2, that is both die have 1s on them, 2 ways of getting a 3, a 1 and a 2, or a 2 and a 1, and so on. I won't go through that list, but if there's any questions on it, feel free to ask. There are 36 possible outcomes of rolling 2 die and 2 dice, and the most probable result is that you get 7, because there are 6 ways of getting 7. None of the other outcomes have that many ways of getting them. And so you can determine the probabilities just by dividing the number of ways of getting that outcome by the total number of possible outcomes, and you get your percentages there. And that's shown in the graph at the lower right. 1,200 dice. If you look, the theoretical points on the straight up and down lines are calculated as 1/36 of 1,200, 2/36 of 1,200, and so on up to 6/36 of 1,200, or 1/6 of them. It was 200 times you would get 7. You'd expect that's 1/6, 16.7% of the time, and so on. And then there's, once again, at least the claim of 1,200 actual rolls of the dice, whether that's simulated, really done, or just drawn to kind of, say, here's something you could get. I don't know, and I don't care. It's just to indicate that, of course, you won't get exactly the theoretical results, but you should get something close to them. And then the question of, is it close enough, is a question that you can answer with advanced methods, but we won't go into that here. So let me stop there for a second. And once again, invite anybody on stage who'd like to come
Are you
up.
stopping to ask questions?
Yes, if you have any.
Well, this is good, because I did do some study on dice rolling, And it is an interesting question whether or not the results you're looking at are reflect of like a random apologies, a random process or not a random process. And the problem is that any possible die outcome is could be the result of a random process, right? If you got snake eyes with 10 dies simultaneously in a single roll, there's no way to rule that out. It's improbable, but so is every other outcome.
That's
So
right. Every single outcome has the same probability, right? Every single instance has the same
yeah.
probability. And that'll be a really great segue into the next thing I'll say, but go ahead.
So when you were saying there is a way to tell, I would offer that there is no binary way to tell. There is only a way of plotting your results against a kind of probability curve. And you could say, well, I got all snake eyes with 10 die. That is extremely improbable. The null hypothesis is that the die I rolled are just a bunch of die with ones on every face, or they're honest die. And the probability of those two worlds is that it's more likely that I have a bunch of die with ones all over them than that I rolled honest die and got all ones.
That's nice. Yeah,
Um,
right.
but how do you draw that line? I mean, do you get to
Yeah.
a 51 percentile where it's more probable X than Y? Like that's a tricky question that you've just posed.
Yeah, no, it is. And I probably misspoke in saying that you can tell. I should have said more like what you said, in that you can analyze them and see if the deviations are deviations that would be expected or not, right? In other words, the deviations themselves could be very low probability. And then you'd start wondering whether something else was going on. But that's a really good point. Jamesy, did you want to say anything? I see you unmuted, but you might just be unmuted at the moment.
I missed most of the room, so I apologize for that. But on the topic,
Oh, we just started.
oh, cool. I love entropy. On the topic of probability, something that I found really interesting is this thing about coin flipping. If you're looking for a sequence, like heads, tails, heads is going to come up more often than tails, heads, heads, and it has, or something like that. It has something to do with like in the split sequence, when you miss, you start the sequence again correctly, so you actually get like a redundancy.
So what do you, I guess I'm not sure what. Let me just. Are you saying that, for instance, if I just flip? I mean, it can't. Let's see. So I'm thinking if you just flipped the coin like thousands of times, and then you just looked at all of the results, and you picked, and you took the first three, and then 2 through 4, and then 3 through 5, and 4 through 6. Are you saying that in that analysis you'd have head, tails, heads more often than head, tails, or something?
I might be getting the sequence wrong, but the idea is that when you miss in one sequence, you automatically start that sequence over. So therefore,
You mean you just have a psychological tendency to? Is that what you're saying, or what do you mean by
no,
starting over?
like the pattern, you're going to find the pattern where the first and the last are the same more often, because like when you miss, it's like if you're rolling for heads, tails, heads, right? You roll a tails, okay, nothing happened. You roll a heads, you get it. But if you roll heads again, you don't like that one still counts. It just only counts as the first in the sequence, rather than actually starting over.
I think I'm not clear exactly on the protocol that you're following to do this.
Maybe you're tossing thousands of times. Maybe I misunderstood, but I think what James is trying to say is that you're tossing thousands of times, and in that 1,000 times, let's say array, you're looking for a string of HTH or THH. So knowing that you've thrown 1,000 times, and then if you're looking for HTH, you will find it more often because you will be finding two H's next to each other. I'm not really sure. In my mind, it should be random, so there's no pattern. That's the definition. But I'm not really sure, Jamesy, where you're going with this.
Well, I think the parallel is like when we're talking about genetic determinism, which is like out of my league. But the idea is when you miss, when you get a wrong answer for producing that sequence, if it counts as the first member of the new sequence, then you get a head start. Whereas if you're wrong and it doesn't count as the next sequence, so it like crunches, that thousands of times gets crunched because your misses aren't really misses, they're just restarts.
Yeah, it sounds to me like there's something more going on than just flip. I mean, if you just flip a coin 3 times and then flip a coin 3 more times and flip a coin 3 more times, I don't see any reason that you should get more heads, tails, heads than tails, heads, heads. In fact, I think I would argue you couldn't possibly.
I think the idea is that some sequences have portions of their own sequence within the sequence and others don't. So if you mess up one sequence, you literally have to start the whole thing over. But a different sequence, if you mess up somewhere, you can you might still have a portion of the sequence, like something like that. I think I know
Yeah.
what James is talking about, and something like that. I'm not sure.
Well, I think that's right. I mean, ultimately, I think it's true too, right? That we are talking about something where there's a protocol that is the thing that actually makes the one more likely, because we are throwing things out or something. We're ignoring some situations. As I say, it wouldn't be really the case that just literally in a string of coin flips you'd find that, but that if you're working, if you have a goal in mind, something about the goal is working. Is working to make the outcome that you're talking about.
The thing that made me think of this is when you're rolling for 7, it doesn't matter what the first dice is.
Right.
Your odds are still 1 out of 6 because there's always going to be a possibility to roll a 7.
Okay, right. That's right. In craps, there are a lot of things like that. That's right. That change the kind of sequence of things. And we've been joined by Ben Tristram. Hey, Ben. Good to see you.
Hey, man, just driving, but I'll be fully attentive in about 15 minutes, something like that.
Okay. Well, we're starting this series. I'm going to have to interface with you when we get to temperature, maybe next week or the week after. We'll see.
Yeah, no problem. Happy to join in. It'll be fun.
Okay, good. Let's see. Benjamin said something which is a really nice. He was talking about what did he say? Something about anyway. I'll just say it anyway. In this sequence that I've got here, you notice that I'm always counting 1, 2 as different from 2 and 1. And those are what we would call in thermodynamics microstates. There are basically 36 microstates. If you just think about taking these die, all the possible microstates that represent the results, there are 36 microstates. And we're organizing those microstates into groups that we would call macrostates. A macro state like 4 would be the macro state, all of which has in the macro state in which the dyads add up to 4. That macro state comprises 3 micro states, the 3 ways of getting 4, etc. But you notice
I think
go ahead.
You were trying to refer to the thing that I said, which is every possible outcome has the same probability.
Right. That's right. It gets very good. That's exactly right. And so we are assuming in here, of course, that because we assume that the macro state 7 is 6 times as probable as the macro state 1, because the micro states all have equal probability. And that's a really nice way of kind of saying it's really it's kind of a postulate of statistical mechanics that microstates are things that have equal probabilities. And it's not easy to justify that, but it makes sense, right? That's why it's a postulate. I guess we could go to Logic Guy for the logic of axioms and all of that. But it's a very common it's an important axiom of statistical mechanics, is that the microstates all have equal probability. but then there's also a question of distinguishability. And I think, let's see, have I gone? Yeah, right. So if you go to slide 4, we'll move on to this. Is 3-4 really different from 4-3? Because if it weren't, then our table of microstates would only have 21 elements in it. There'd be 1, 1, the one way of getting 2. There'd be 1, 2, the one way of getting 3, etc. And you'd have a very different probability distribution. I show it over there on the right with the red bars. Both 2 and 3 have a probability of 4.8%. Both 4 and 5 have probabilities of 9.5%. 6, 7, and 8 all have 3 ways of getting them. In this way of thinking about things, they'd all be 14.3%. So I should expect my distribution to be kind of this very coarse step. One step, a step up, a kind of a bigger step at the top, and then a step down and a step down. And observationally, we just see that the observations of rolling 2 die don't comport with that. It appears that 3-4 really is different from 4-3 because our only n with our hypothesis of equal probabilities for microstates do we actually get the macrostate distribution that's shown here with going up kind of in a linear fashion up to 7 and then coming down in a linear fashion back to 12. So there at least seems to be observational reason to say that that we can basically label the die. This is going to be important later on, but really important when we get to quantum statistics, if we get to quantum statistics, which I kind of hope we do down the line, maybe in the 3rd or 4th week, if this goes on that long. The question of distinguishability versus indistinguishability, and we'll return to that in an important example at the very end today as well. Die appear to be distinguishable. It matters which one is the 3 and which one is the 4, so that when the other one is a 3 and the other one is a 4, that's a different microstate.
Maybe an easier way to think about it is that if you have 2 dice of 2 different colors, so getting 3 blue and 4 red is not the same as getting 4 red and 3 blue. This is a totally different situation.
Right, that's a really good starting point, right? You could color them differently. You could just take a chip out of hopefully a face. I guess you wouldn't want to take a chip out of a corner because that would make them non-fair dies probably. But you could mark on one face with a marks a lot and then distinguish. You could do anything to distinguish one from the other. And if that somehow changed the outcome, wouldn't it be interesting? You start with 2 apparently identical die, and you get the probability distribution that I show in red here. And then you put a mark. You take a marks a lot and you mark one of them. Now you can tell which one is which, and all of a sudden the rolling probabilities change. Wouldn't that be interesting? But it is an important thing, and we'll see that in quantum mechanics, one electron is literally indistinguishable from another, so that when you switch electrons, you can't tell that you've switched electrons. And it means that any statistics that involves thinking that electron 1 is here and electron 2 is there, it can't be different if electron 2 is here and electron 1 is there. Those are the same state.
Can I object to that?
You can. Oh, I know you. I expect you to object to it, Benjamin.
Well, the objection would be basically that that quantum crypto wouldn't work if electrons were fully fungible.
What you want to know, buddy?
Yeah, I don't know what that. I didn't follow that one.
I think it may have been a joke.
I hope it was. You never know.
No. It's not a joke. It's not a joke.
It is a joke. Trust me, as somebody who understands crypto quite well. It's either a joke or deeply ignorant, or I'm deeply ignorant. One of the 3. You'll have to defend it.
Let's take a moment and hear the defense. Yeah, go ahead.
Quantum communications, quantumly encrypted communications requires sending, let's say, a photon down a fiber, but we could substitute an electron if you insist, in an entangled state. And once that photon has been entangled, it can't be captured by a sensor that detects photons and re-emits another photon. If that were to happen, even though you get 1 for 1 photon, the resulting photon would not be in an entangled state, and consequently, the cryptographic connection would break.
Well, I think that's actually, I don't know what Ben thinks. I find that kind of a compelling argument in the sense that I don't have an immediate answer to it. But I guarantee you there is one, because electrons are indistinguishable. The statistical results of statistical mechanics gives the wrong answers if you assume that electrons are distinguishable. So while I don't know the answer, while I don't have a response to you, Benjamin, I know that you're wrong, but I just can't tell you why.
Well,
go ahead, Ben. Do you have a better way?
That's a solid starting point.
So yeah. So firstly, when I got all excited in the beginning, is because I thought he was talking about some scammy shitcoin. When he said crypto, I thought you meant cryptocurrency rather than cryptography. What I don't have a one-word answer either, but what I do know is that you can't in the current proposed and tested quantum cryptography, you cannot detect the interception of a single entangled particle, whether it be a photon, electron, whatever they're using. It's just you only detect that somebody is eavesdropping on a statistical basis after a period of eavesdropping, and I believe it's fundamentally impossible to detect. I don't know if it's impossible to detect one, but that's not how the systems are set up. They're set up to detect a continuous eavesdropping, which causes a statistical skewing in the spins that you receive. Beyond that, I don't know the exact details, so I can't tell you the answer in detail, but I'm sure that bit's right.
Yeah, and I was just looking to see if anybody smarter than me had a response for Benjamin. I didn't find that, but I do see Wissam talking about the central limit theorem, which I debated, actually talking about specifically, and maybe we'll get to that. It comes up pretty quickly here, so maybe I will return to that. Anyway, that is really an interesting thing in and of itself, although a little hard, I think, to explain, because you're talking about the distribution now of a statistical property, i.e. the mean, that's calculated from a distribution that can be of any form. So that's, anyway, now I've already said more than I probably should at this point, but maybe we'll get back to that. Thanks, Wissam. Okay, let's see. Let's move on then to, let's see, did I finish that? Yeah, I did. Okay. So let's move on to 3 dice. It's interesting. A few people have done this. Turns out to get pretty complicated to work out the probabilities for a large number of dice throws. And so I won't go any further than to show you this distribution for 3 dice and just to kind of see the direction we're headed. When we throw 3 dice, there are now 216 microstates, 216 possible outcomes, treating the dice correctly as distinguishable. And of those 216, there are 16 macro states. You can get a 3, 4, 5, 6, all the way up through 18, 16 possible macro states identified by the sum. One of them, macro state 8, has 21 microstates. You can count them up there. They show the values of the 3 die in each of those cases. There's 21 microstates that have sum 8. And the most probable sums correspond to those macrostates 10 and 11 that have the most microstates. And those have, what did I say? I guess I didn't write it down. What is it? It's 20, 21, 4, 26, I believe. 26 microstates in each one of those. And those are, let's see, did I say it before? I guess I didn't. No, okay. No, wait a minute. Now I'm confused because I thought I had brought up the concept. I guess I didn't bring up the concept of entropy before, but so I guess I am just doing that now. The highest, so entropy is a property of these macro states. Entropy is high entropy macro states are macro states that have have more microstates than low entropy microstates associated with them. So the macrostate 3 is a very low entropy macrostate because it has only one microstate associated with it. And this is, in some sense, this is the idea of entropy right here. It's just that. Macrostates that have lots of microstates associated with them. If the surface on which the dice, if I have 3 of these dice, if it's jostled, the microstates will change, right? It could be in any one of them. If I jostle the surface with equal probability, the 3 dice could end up in any one of those 216 microstates, but very rarely, of course, will it end up in macrostate 3 or 18 because there's only one microstate associated with it. It will spend most of its time, the dice will spend their time in macro states 10 and 11. But we certainly can't say that this is a system for which the sum is 10 or 11, because there's a very high probability that it'll be something other than 10 or 11. That's one important point here, is that while 10 and 11 have the highest probabilities, it's much more probable that it'll be in something other than 10 or 11. We wonder what happens. So this is a very broad distribution. If I simply talk about, and notice, by the way, that 10 and 11 are centered on 10.5. 10.5 is 3 times 3.5, because if you roll a single die over and over and over and over and over and over again, if you do that 1,000,000 times and add up all the results, the result should be pretty close to 1,000,000 times 3.5, because any single die rolled over and over and over and over again will on average give you 3.5. Right? Even though it'll never give you 3.5, it will on average give you 3.5. So the question is, why, at what point you see it narrowing in here. When we rolled one die, a 3.5 was kind of the average, but it had just as much probability of being anything else. When we rolled 2 die, it started to narrow in on 3.5. And now it's narrowing in even more, because you notice that the tails of the distribution comes down faster from the top than it did before, so that it can tail off at the ends as it does. It doesn't tail off a lot, but it does a little bit. So on the next slide, I'm just going to try to convince you that as I make n bigger and bigger and bigger, that narrowing will continue, and this should just make sense. I'm not going to go. You can actually show that in cases like this, that the distribution will narrow in a way like this. So that if I now plot the probability density of different averages, notice now that if I were to roll the die, 1,000,000,000,000 times, let alone 10 to the 23rd times, my average could be just about anything, right? It would have to be n divided by 1, 2, 3, 4, up to 10 to the 23rd. So there's only certain values that it can take on, but those values are now very closely spaced. There's 1,000,000,000,000 or 10 to the 23rd possible averages that I could get, or more. The average, however, the most probable average, however, will narrow in on 3.5, like I'm showing here. So for a small number, you'll have a fairly broad probability. That might be at small n doesn't look very different from 3. Could be, maybe that's 5 die or something like that. And then as I increase, the green curve is a larger number and the red curve is a larger number yet. In all 3 cases, the area under that curve is 100%. And so a couple words about a graph like this. Notice I'm graphing probability density, not probability. This is probability density. It's kind of probability per unit average value. So I might have what's the probability of getting 3.2 to 3.3? The probability of getting a value over a range of 0.1 centered on 3.2 or something like that. What's the probability of getting that a value centered on any particular value with a given range? So I have to know the range. It's a probability density, and that is reflected in the fact that the area under each one of those curves is 100%. So that as it gets taller, as it gets sharper, it has to get taller so that the probability, which we get by, in the language of calculus, integrating under that curve, the area of that curve represents 100% because it's got to be something. Boy, did I ever not say all that very well. Anybody want to take a stab at it or ask a question to make me say it better?
It was pretty good. Are you just playing with numbers? Can you try 250 die?
Can I try what?
250 die.
You mean you want to know
the average for a single die rolled 250 times?
Oh, well, 250 times 3.5.
That's not the
So that's
average.
getting pretty close to 1,000. Sorry?
That's not the average.
Why do you say that?
The average of a single die rolled.
Oh, well, what I mean by average is what I say down there. The sum of all of the things divided by the number of rolls or the number of dice if you roll them all at once. Is it just not understanding what I mean?
I guess I was trying to ask what the probability distribution is for 250 rolls.
Well, I don't know. I don't know what that is. In fact, that's kind of complicated. I assume, is there a form? I mean, I don't know that there's unlike, for instance, thing like the binomial expansion, it's a little different with 6 die. I don't know that there probably is. Maybe somebody else knows. There might be a general formula for the probability distribution for n rolls of 6-sided dice, but I don't know what it is. I don't know that we know what it is. We probably must. Somebody must. But I'm not sure I'm understanding your question though either. I certainly can't tell you what the probability is, but I can tell you that it centers on 3.5. If I take the total of all the pips on the die and divide by the number of die, I'll get 3.5 pretty much. I will be close to 3.5.
The question to ask here is how far off of 3.5
right
would it have to be for you to start to suspect that the die were not fair?
No, that's a really good question, and I'm not going to address it here. That kind of question can be addressed. That's easier to address than the first question. At least it would be easier for me to address than the question of what is the distribution for 250 die. As you go to a larger and larger numbers, this thing does approach a Gaussian, and the standard deviation of that Gaussian is easily calculable. And so while I can't answer, I don't know right now what it is. That's one that I could figure out in short order, and it certainly is well known. And it's exactly the right question. The point is, how big a deviation from 3.5 would you expect? And it's related to the question of when I measure the pressure in a gas, and I recognize that it's the result of these collisions against a surface, then the question is, how much might that pressure actually fluctuate? And then the answer to that question is going to, number one, it's going to depend on the area over which I'm measuring the pressure. It's a very small area. It's going to have wild fluctuations, but a larger area won't, simply because of the statistics. But I can answer questions like that in terms of the numbers of particles that are hitting per unit time. What you have to kind of ask, okay, what's the time frame? Am I talking about the pressure over the course of a femtosecond, or am I talking about the pressure over the course of a second, or a tenth of a second? Lots of questions come into play, but they're all answerable in terms of the statistics. And the surprising thing, I guess, is simply it shouldn't be that surprising, but when you are talking about numbers, either of collisions or of particles or whatever, like 10 to the 23rd, the answer is those fluctuations are damn small, really small. And for our purposes right now, that'll suffice. But those are really important questions, and the topic of fluctuations in statistical mechanics is central, and not something we'll spend much time on here. So yeah, good question, and I will summarily move on from it. So let's go to slide 7. Now I'm going to talk about a slightly different question, which will lead to the last thing I want to talk about, which is this distinguishability thing, putting molecules in a box. Now there's an awful lot going on here, and quantum mechanics has a lot to say about the number of ways you can put molecules in a box, which has to do with kind of dividing both physical and momentum space into little Planck constant sized cubes, and treating to know kind of how many places you can put a molecule. How many places can you put a molecule in a box? Well, it turns out that you can actually kind of talk about that question meaningfully. We're not going to get down to the quantum level here. I just want to treat kind of a simple case where I have a box. I'm going to put each of n gas molecules either on the right side, the right half of this box, or the left half of the box. Not just the right side and left side, but the right half and the left half. Each side has the same volume, so we'll use that as a justification for flipping a coin to decide where to put each molecule. I'm going to put a molecule on the left if it's heads, and on the right if it's tails, or something like that. So just the simplest situation. All sorts of questions should occur to you before we get to the end, 2 slides from now. So let's just look at the probability of having a fraction f of those n molecules on the right side as a function of n. I've got a graph there, but let's first just look at the 2 things. So if n is 1, the only 2 values for f are 0 and 1. There's either nothing on the right side or everything on the right side. And both of those have a probability of 50%. So this looks a lot like the rolling the single die and having a flat probability distribution. There's only 2 possible results, and they have the same probability. Those 2 possible results are f is 0 and 1. If I have 2 molecules, the only possible values for f are 0, 1/2, and 1. I can have nothing on the right side, I can have everything on the right side, or I can have half of those things on the right side. And so I show you the probabilities, and notice that once again I'm treating putting the first one on the left and the second one on the right as different from putting the first one on the right and the second one on the left. So if that's the case, if that's a reasonable thing to do, then the probability distribution would be slightly higher in the middle than it is on the ends. 25% on the ends, 50% in the middle, etc. With n equal 8, there's only one way to put none or all of them on the right, but there are now 70 ways of putting 4 of them on the right. So that giving you an F equal 0.5. I'm just saying that you can get out a piece of paper and see if you can somehow enumerate or graphically illustrate the fact that there are 70 ways of putting 4 of those 8 molecules on the right. That's what's called number of combinations of 8 things taken 4 at a time. And my calculator, probably your calculator too, has a button. You can put in 8 and 4 and push that button, and it'll tell you 70. Okay, and so as n becomes large, we get the same kind of graph we had before. Macro state F equal 0.5, right? The one consisting of all microstates with half on the right has the highest probability and the highest, quote, entropy. Right? It's the one that is the most probable because it has the highest entropy, the largest number of microstates. And when you get to 10 to the 23rd, that macrostate 0.5, if you notice in addressing to some extent Benjamin's question about how much fluctuation are you willing to tolerate, when you have n equal 8, a macrostate of 0.4 or 0.6 is going to be very common. You're going to see 40% of those 8 molecules on the right very often, probably see a quarter of them on the right very often. You'll probably even see none of them on the right pretty often, in the sense that it'll happen. No question it'll happen. But it's surprisingly enough, one can really make statements like this when you have 10 to the 23rd molecules. While there is a microstate, there is an accessible microstate in which all 10 to the 23rd are on the left and none are on the right. And while that can, in theory, happen, I can guarantee you, I can bet my life on the fact that it will never happen. You are in the sense that you could take me up on that bet and then sit there and watch it with a reliable video recorder, because I wouldn't want to bet my life on something that wasn't proven to me. But I would feel absolutely confident in betting my life on the fact that you will never see all 10 to the 23rd molecules on the right. Moreover, I could even, with a little more statistical analysis, I could probably be a little surer of this. But it's likely the case that you will never see 40% of those 10 to the 23rd molecules on the right, or 60%. The kinds you would have to, if you looked, it's the kind of, you say things like this: if you looked every tenth of a second, you looked at the molecules every tenth of a second, just to see where they are, et cetera. Took a picture every tenth of a second. You'd have to wait. And I haven't done this calculation, but I'm guessing it would work out this way for 10 to the 23rd. You'd have to wait many, probably an incomprehensible number of ages of the universe before you'd ever see 40% of them on the right or the left. Those are the kinds of numbers that you get when you get to 10 to the 23rd molecules. And that's a little surprising. I think some people would be a little surprised by that. The statistical calculations get surprisingly low fluctuation at that level. So let me stop there for a second. Okay, so the last thing I want to talk about is the so-called entropy of mixing. And as I said, and this gets at what the second law. So I've defined entropy for you, and now we can talk about the second law of thermodynamics, one statement of which is that the entropy of an isolated system will increase if it can. So if I have an isolated system, that means that I don't do anything. It's inside of walls that I can't move, that I can't poke anything through, that I can't let heat flow through. This is a system that is isolated mechanically and thermally from its environment. No heat flows into or out of it, and no work, we say, is done on it. No mechanical work can be done on it. So the entropy of an isolated system will increase if it can. So here's an example. I have two gases, a red gas and a blue gas, on sides of a box with a membrane separating the two of them. And they're obviously, the red gas is different from the blue gas. I shouldn't say obviously, I'll specify that. The red gas is different, it's not just labeled differently, it is different. It really is red if you want, and the other one really is blue if you want. And it's isolated in the sense that that outer wall, forget about the membrane, but the outer wall is impervious. Those walls can't move. Nothing can poke through them. No heat can flow through them or anything. So that is an isolated system. Now it has a certain amount of entropy because of the way I've put blue and red atoms or molecules into that box. And you can see, I think, that in going to the picture on the right, where I've removed the membrane, or maybe I poked a hole in it or whatever, I now have, I hope you can see that that's a higher entropy system. Let's talk about that in a moment, maybe. And so that my starting point is a point, has a certain entropy. Let's just say that the initial separated gas has a certain entropy. Now, can that entropy increase? Well, I don't know. Apparently not. That's what it is. But if I poke a hole in it, I'm allowed to kind of come in and poke a hole and then leave. So I'm gonna either poke a hole in or remove the membrane. I like the idea of poking a hole in it and then go away. So I'm gonna poke this hole. It's gonna be a very small hole. Only one atom at a time can move through it, let's say. But then I go away. So this is now really is an isolated system. It pretty much looks like it does in that picture, but there is a hole in the membrane. And so over time, that system is going to, I think we all agree, it's going to end up looking more like the other system, whether or not the membrane is still there. If there's a hole in it, then there's going to be a mixture of red and blue on either side. And the reason for that in the language of statistical mechanics is simply because that's a macro state of the system that has far more microstates associated with it. There are way more ways of putting red molecules around mixed with the blue molecules than there are of putting all the red molecules on one side and blue molecules on the other. The specifics of how we'd actually calculate that are a little tricky and maybe even require quantum mechanical ideas to do these ideas about how you divide up spaces. And there's a lot more things going on here. I haven't even really specified some things I probably should. But I just wanted to point out that, give this as an example. Clearly, the final state here is a final state that's more likely. And the reason for that is because there's just way more ways of putting those red and blue molecules in that kind of a configuration than there is in putting it in the original configuration, whether or not the membrane is there. I can now kind of just forget about the membrane. There's a hole in it. I might as well remove it. I can still imagine the system returning to that initial state. It just seems extremely unlikely. And it is. It's unlikely to the point that I would bet my life on it if we're talking about 10 to the 23rd red molecules and 10 to the 23rd blue molecules. Okay, so I'll just stop there before going on to the final slide. Any comments, questions?
May not be the right time, John, but it'd be quite fun to think about if you left that hole there and devised a machine that could only let through fast-moving molecules.
Right. What would we
Never
call
got it.
such a machine?
Well, I'd call it Maxwell's demon, but I don't know what you'd call it.
Yeah, yeah, that's right. And there's another topic I hadn't really even thought about talking about, but probably worth spending some time. My kind of brother of a different mother, colleague Harvey Leff, wrote a book called Maxwell's Demon, and so he was a kind of a lifelong fan of Maxwell's demon ideas, and it's led, thinking about that has led to all sorts of interesting insights and information. It's Shannon entropy kinds of things, and the heat associated with entropy. Well, I didn't say that well, but anyway, what Ben is talking about is just exactly that. Imagine you had a sentient being who sat there at that little hole and simply closed a trap door whenever a red molecule was moving at it from the right to keep it on the right, opened up that trap door when a red molecule was moving at it from the left to get it over to the right, and kind of vice versa for the blue molecules, right? An intelligent being could operate a trap door and get it back to that low entropy initial state. And the question around this Maxwell's demon idea is, how is that consistent with the second law of thermodynamics? And the answers that people have come to have to do with, of course, considering the entropy of the demon himself and what happens in the process of operating that trap door. Gets into some really interesting theoretical territory. Anything else on that, Ben, or did anybody else have anything?
No, I just thought it'd be an interesting time just to at least bring it up, because a friend of mine
Yeah.
independently came up with that. He said, well, I've developed this heat pump that
Oh.
can just, and I'm like, dude, this is well thought about. Well done on you for coming up with it independently, but it has been well studied and considered. Yeah, I think
Right.
the bottom line is that whatever that sentient being was doing, it would give off more heat than the good it can do, basically.
Right. And it's important to say in these things, the isolated system is important, right? I can take that final state and I can put it back in the initial state. But I can only do that by doing work and or heat. You have to do it with some kind of a process. And when you watch the process, you find out that when I take that final state and I take all those molecules and I move them back into that initial state, I can only do that if I somehow let the entropy of the exterior universe increase in an amount equal to or greater than the decrease of entropy that I affected by moving the final state back into the initial state.
There is one other thing that might be fun to explore here, John. Imagine we put an apple in a box, for example, and we let it rot. And then we wait forever. Surely it would reform into not only an apple at some point in infinite time in the future, but into every other thing that could be made out of the same molecules as an atom. You just have to wait long enough, right? You put an apple in a box, it rots, becomes mush, turns into eventually pretty much gas, and then at some point it must reform into an apple.
Yeah, I guess that's true. I mean, it's certainly true that is an accessible microstate of the system, right? It has the same energy, the same number of molecules, same number of pieces, etc. It's just another version of the broken egg, right? If I
It's
same
set to
kind
measure
of
zero
thing.
again, I think, as well.
Yeah, right.
It's certain to eventually do it, but the probability of it doing it in any given amount of time is zero.
Right, certain to eventually do it, but not in the age of the universe. That's the difference.
Yeah, not even close. Yeah, but
Yeah.
it's pretty interesting to think about.
Yeah. Okay, so the final slide for today is just a thing. I just want to kind of tickle your fancies with a thing called Gibbs paradox. This was a paradox of classical thermodynamics, which is answerable using statistical, and especially in quantum mechanics, using quantum mechanical methods. And it has to do with this distinguishability idea. So take the same system we had before, gas on the left and right, but now make it the same gas. They're all oxygen molecules, and now poke a hole in the membrane and let the gases mix. Right? You are letting them mix, and you end up with something. It looks like you could just put the membrane back, and you'd have the initial state again. So what happened? I mean, I poked a hole. I was isolating those molecules on one side. There's a molecule on the right side there that probably is on the left side. Well, there's lots of molecules on the right side in the initial situation that are now on the left side in the final situation. Has the entropy increased or not? Are there more microstates? It looks at first glance like there's more microstates because every one of those molecules can now be placed anywhere in the entire container, whereas half of them had to be on the right at first and half of them had to be on the left. So has the entropy increased or not? And the answer is that essentially no. There is actually a slight effect, but to a large extent, the entropy does not. So there, and it's a quantum change. If I take hydrogen atoms and oxygen atoms and mix them, the entropy does increase. And you can actually measure the entropy in various ways, chemical processes, etc. There is no entropy of mixing when the two sides are filled with the same atoms. And that is a testament to the fact that one oxygen atom can't be distinguished from another, not because we can't distinguish it, but because it is literally indistinguishable. And that's kind of an important point too. It's not just that our powers of distinguishing things are limited. It's that the statistics can only be the way they are if there really is no difference between one and the other. No physical reason to say that one oxygen atom is a different atom than another. They're just all oxygen atoms. So what other things might matter? I mean, there's all sorts of things we could say more about. I'm done now, but we might start our discussion if anybody has any comments about this. There's a lot of things I didn't say about the initial situation here that really would matter, and some other kind of interesting minor effects that actually do end up making a difference, even in this case. For instance, what if I told you that the oxygen atoms on the right side of that container were moving on average twice as fast as the oxygen molecules on the left side of that container?
So a temperature imbalance?
So they weren't, yeah, in other words, basically that's saying that the temperatures weren't the same. I never said anything about the initial temperatures. And then, of course, there would be
a homogeneity can be exploited for energy extraction. So it means that the entropy is not optimized.
That's right. So there's no paradox in the case of one side being initially at higher temperature than the other. When they mix, they will come to a common temperature, and that common temperature will reflect the fact that the entropy of the system has increased as a result of that. There's another subtle way in which things are different afterwards than they were before, even if the temperatures are the same, the numbers are the same on both sides. And that has to do with the fact that when the wall is there really were N molecules on each side. And when the wall isn't there, I've removed that restriction, right? I can have slightly more molecules on one side than the other. There are more accessible microstates afterwards than there were before. But that's a minor thing to the extent that the number of molecules on each side is allowed to be different simply by the distribution in the final state, right? That final state can have more on the left and the right, more on the left than on the right, but it can't be very much more. Or at least I shouldn't say it can't be. It won't be in most cases. So these are subtle things. It's not quite clear how you even take them into account. I should make that clear too. Anyway, there's a link there to the page that I took these last two from, and it talks about Gibbs paradox a little bit, the whole kind of paradox of distinguishability. And as I say, I'm done. So, I'm sorry, Joe's down there, Allie's down there. Or are they? Are they up here yet? My club deck never actually tells me who's on stage. Yeah, welcome, Ali. And then Joe, maybe I see Ali first on stage. Did you have any comments or questions?
Yeah, John, I have a comment that perhaps could be presented as a question. So the way I think about this in terms of the entropy, at the very simplest form, is thinking that there are two buckets of energy in the beginning of the universe. Let's call them entropy, and the other one would be enthalpy with an L. So the first bucket, the enthalpy bucket, this is a bucket that, and I'm not quite sure if I'm saying this correctly, but the bucket is total amount of available energy to do work. And as universe expands and things are created, then the enthalpy with an L, it decreases with time. So as everything moves from, say, the order, of course, to a disorder. And now the entropy, being, of course, the bucket, which is the total amount of energy that now is being used to do work, and that goes into that bucket. So that, spent energy is no longer available to do any kind of work. So by the time the universe does what it does, and the entire kind of universe comes to an end, so the bucket of entropy is completely full, and the bucket of enthalpy with an L is completely empty, and that's what we call that the dead heat. If this would be too, I fully understand. This is really a simplified way of talking about this concept. But does that kind of make sense to think of it this way? These two buckets?
I mean, I think it gets at the right ideas. I don't know how to. I'm not sure. For the long time, I thought you were saying enthalpy with an L. I thought you were saying entropy. I thought that's what you meant, but you were saying enthalpy, the thermodynamic energy idea, right?
Yeah, that's correct. Yes.
Yeah, right. So a lot of thermodynamic concepts get a little confusing in cosmological models. A lot of time is spent trying to figure out what happens, for instance, if the universe does eventually turn around and contract. Does it just kind of retrace its steps in a contracting universe? Does entropy decrease maybe? And of course, I'm sure you know about all the conversations connecting the increase of entropy with the arrow of time. So there's all sorts of questions like that. That's not central to your question, but I just wanted to point out that when you try to apply thermodynamics to the universe as a whole, it's not completely clear that that's a fair thing to do, because is it a closed system really? Is the fact that it's expanding mean that it's doing work against something else? Is energy really conserved in the universe? These are all questions. But I think, as Benjamin was just saying, one of the best ways, I think, of thinking about heat death, if you want to think, I think that's kind of what you're pointing at, the idea of what's called the heat death of the universe, is just that as long as there are inhomogeneities of any sort in the universe, those inhomogeneities will strive to become homogeneities, and those that's just kind of a fundamental thermodynamic idea. And of course, we can exploit inhomogeneities. Conscious beings can exploit inhomogeneities to do useful things, etc. But if they don't, they'll still disappear if they can. And presumably in a universe that has full access to other parts of the universe, that comes in contact with other parts of the universe through mixing and through heat transfer, through the coming to thermal equilibrium, all inhomogeneities ultimately get erased. Now, when you also fold in the fact that there's energy locked up in hydrogen that can be exploited through fusion, it becomes a little more complicated. Can we guarantee that at the end of the universe we will have fused all hydrogen to helium? I don't think anybody thinks that's the case. So even at the very end, you would imagine there is still energy around in the form of hydrogen atoms that could be fused to helium, but maybe there's no more mechanism. There's not enough density around to form new stars. Perhaps I don't know. I think you have to. Maybe that's a silly thing to say, because there'd always be a density enhancement somewhere that would eventually draw hydrogen together, eventually fuse it to helium. But I think all of these are kind of open questions. And I don't know.
Sure, John. I think I should have probably qualified my question or my comment by first saying that let's assume the universe is a closed system, number one. Mm-hmm. Number two, when I think about the buckets, I mean, literally just a metaphor for the placement of the energy at the beginning of the universe. And these two buckets, they are open buckets in a sense. Again, I'm making these things up as I'm talking. Mm-hmm. Comparing this with two buckets, the space that you talked about with the membranes, compared to the membranes that it does not allow any kind of a movement of let's say the molecules from one side of the box to the next. So in this case, I can't have this membrane between these two mm-hmm. spaces. An initial formation of the universe, one side being completely full of let's call it energy, of course, and then the other side is completely, empty. So then, I guess this way of thinking, it takes us to the death heat of the universe. So anyway, I should have kind of qualified this. Again, I'm making these things up as we go along in terms of thinking about this concept.
Yeah. Well, this is all kind of interesting speculative stuff. I don't have anything really concrete to say, and I think maybe it moves a little further on. I like to kind of keep these things as much as possible on kind of well-established elements of thermodynamics itself in this particular case. So, I think if that's okay, I think we'll call that good and ask Joe if he has any comments or questions.
I think it's fascinating that you can take a space and you can dehomogenize a space with frequency.
Oh, what do you mean by that?
So, for instance, they do that with galenium when they're aerosolizing galenium to make semiconductors, the chips. They send a radio frequency with a certain hertz, and that way it's not homogeneous, it's more predictable in where the galenium will be.
So so now I don't know at all what you're talking about exactly, but is this something where they create kind of standing electromagnetic waves to guide things somewhere?
So essentially, imagine that instead of you just have the box, you're applying energy or something to the environment. You can once again create non-homogeneity by applying outside work, even though that you never even opened the box.
Oh, right. Yeah, and of course a really good example of that is an air conditioner, right? I can move, or a heat pump, right? I can literally move heat from the cold outdoors into my warm indoors by using work. And I can pay for that work. And what I get for that work is every ounce of that. So if I pay for a kilowatt hour of energy from the power company, and I get 2 kilowatt hours of heat into my house, because 1 kilowatt hour that came from the power company came in as heat, and another kilowatt hour of heat came in from the cold outdoors into my house. That sounds like magic, but you can do it because of the way entropy works, which maybe we'll get to too. God, there's so many things. As I go through this, I'm thinking this may end up being a 10-week sequence. Who knows? But that's right. I mean, it sounds like it's just another example of that one. It's not to say that you can't order systems. You can, but you have to do so. You have to do some outside work. You have to turn some useful energy outside into unuseful energy, because every time you do work, you do so at the expense of waste heat, basically.
I did enjoy today's dice are not treated equally, and it sounded very fundamental, very first order, like.
You mean the distinguishability versus indistinguishability thing?
Right.
Yeah. 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 Let's see. There's something else you said that reminded me of something, and now I'm forgetting that. But anyway, anybody else have any comments or questions?
I'm not sure if this is gonna be discussed like if this is today's topic or some other times. But my previous understanding was, and maybe here you can expand on this and tell me whether this is accurate or not. As you put particles into a space, let's say a box or some sort, as you have here on your last slide. The bigger the space, of course, the bigger the box, the more places those particles can be. And the more particles you put, then the more ways those particles can arrange themselves as well. But then it gets complicated here because there's attractive and repulsive forces between the particles and all that stuff. So is there a point where if you put too much stuff, it becomes lesser entropy? Like by adding more stuff, you kind of get rid of, you know what I mean? Like because I'm just taking them naively like that. I don't know.
Can we please put in hydrogen and pack it in there to the point where one of them, no longer do you get hydrogen gas, but you end up decaying into an individual atomic unit, and it phases right through the membrane wall.
Well, it's okay. So I thought I knew where you're going with that, but I'm not sure what you mean by that exactly. I thought you were going to the point where they were so close together that they fused to helium or something. But
so if we took hydrogen and we put it in a standard metal,
you're talking about hydrogen fatigue or something.
Yeah, it literally goes through the wall and it travels through, and then 2 molecules of hydrogen end up recombining in the middle of the wall and then create hydrogen fatigue because you have little gas pockets in the metal wall.
Right. Well, the thermodynamics of that, I guarantee you, is beyond my brain right now. I'd have to have somebody explain that better to me.
No different than pH of water being neutral at 7. Some of it is on this side of the box and some of it's on that side, but at all times it's kind of equal. It's just like pH.
Ben,
hydrogen
did I see?
Splits apart just like pH.
Oh, sorry. I thought I saw Ben unmute for a second. I know maybe you just
I didn't. I'm trying to follow as well.
Up. Maybe you just thumbed up.
Yeah, no, I thumbed up what Samash was saying. The question.
Okay, let's see. So, all sorts of things. I should be writing down these things to talk about in the future. There's so many things that have occurred to me while you guys have been asking questions, and then I instantly lose them. Yeah, anyway, rather than try to do that, I'll write down more ideas over the week. I can see this is going to go on for a while. I think probably next week, but I have in mind, and you might want to think about this there's a thing called an Einstein solid, which is a really nice metaphor for thermodynamics of materials in general. And the idea is that in quantum mechanics, when you have a harmonic oscillator, that harmonic oscillator has energy states, quantized energy states that are separated by a constant amount, delta E or something you can take, whatever that chunk of energy is the same. And so a nice model for getting into statistical mechanics is thinking about an Einstein solid made of some number of these elementary oscillators. So one oscillator will take 1 unit of energy or 2 units of energy or 3 or 4 or 5, any number of units of energy. Each oscillator will do that. And so I can have interacting systems. Now, first of all, I have a system into which I want to put, let's say I have a system that's made of 3 of these oscillators, and I want to put 2 units of energy into that system. How many ways can I put 2 units of energy into 3 Einstein oscillators? Well, I can put both units in all 3. That's 3 ways. I can put 1 unit in one and another unit in another. I can do that in 3 different ways. And that's it, right? So what's that? 6 ways that I can put 2 units of energy into 3 Einstein oscillators. And then you start kind of building up kind of understanding of how the number of microstates increases with the total energy. If I put 10 units of energy into 3 oscillators, there's all sorts of ways I can do that. And the number of ways you can do that increases kind of surprisingly rapidly. And then you talk about one Einstein solid made of 3 oscillators interacting with another one made of 2 oscillators, sharing energy back and forth, but doing so so if I put 6 units of energy, say, into the total system, I have a 3 oscillator system and a 2 oscillator system. I put 6 units of energy in there. How is that energy going to be shared between the two? It'll be shared in the way that has the most microstates associated with it. And you start counting those up. You can count them up if you have 3 and 2 and 6 units of energy. But it's surprising that by the time you get to one Einstein solid with 200 oscillators and another Einstein oscillator with 100, another Einstein solid with 100 oscillators, and you put, say, 50 units of energy in, or maybe 100 units of energy in, this is no longer a calculation that you can do on your calculator or even with Excel or anything else. The numbers just get too big. You're already at numbers like 10 to the 200th or 10 to the 300th when you start doing the calculations involved. So you need new methods if you want to talk about Einstein oscillators, not of 100 and 200, but of 100,000 billion oscillators interacting with another solid with 100,000 billion oscillators. That is to say, kind of 1 mole, a gram of hydrogen interacting with another gram of hydrogen, kind of effectively that kind of a system. These are very small systems, but they have numbers that are fantastically large, so large that you end up having to talk about, you have to define entropy properly, which involves a natural logarithm, which goes a long way towards taming these big numbers. You take the logarithm of 10 to the 23rd, and now you're talking about 10 to the 23rd, which is fantastically smaller than 10 to the 23rd. So anyway, a little taste of where I think we'll probably go next week, and Ben may not recognize it or not, but doing so and looking at kind of the equilibrium between pairs of Einstein oscillators leads to the concept of temperature and the idea of temperature as a derivative entropy with respect to energy. So we'll see, maybe see how that, I say a derivative, but we'll just talk about in terms of slopes and things. Anyway, that's kind of a little taste of, I think, where we want to go next week. And I'll take the suggestions that have come through. I'll have to listen to this again to remind myself of all the little things I should have talked about. Maxwell's demon, the actual kinetic definition of pressure, kinetic theory, as it's called. That's another kind of elementary form of statistical mechanics. Go ahead, Joe.
That's an amazing segue. To
Okay.
remind people, because where are you going to watch this, John, again, if you want more information, if you've missed something?
Oh, yeah. Are you fishing? That's right. If you do want to listen to this again, of course, you can listen to replays here on Clubhouse. But in addition to that,
Jesus, John.
In addition to that, you can go to Shamash's page, which he's linked to. Let's see, looks like you just put it up again.
Yeah, I put it in chat again. This is the Scientific Discourse YouTube link. If you missed a room, or if you want to refer to it again, or show it to your friends or anything, these episodes will hopefully be, let's say, starting next week. This one will be certainly online.
And here's the plus about doing it that way is that Shamash turns the pages for you. So you get the audio and you get the slides showing on the YouTube without having to go to any effort yourself. Is that a fair summary of why one would want to do that, Shamash?
Yeah, that is a fair summary. Thank you very much for that.
Yeah. No, thanks for doing all that. I'm totally indebted to Shamash because I would never go to that kind of trouble, and I don't want him to feel like he has signed on for all the way through Beta Physics number 1000 several years from now.
Hopefully several years from now, AI will take my job.
That's probably right. Joe, I know I saw you unmute too. I don't know if you have another comment. I think maybe we'll start winding down.
You might enjoy the rabbit hole of going down PV equals Z nRT.
What's that?
Instead of the ideal gas law, it's when you go non-ideal.
Oh,
and a compensation factor
where
for
Z is a function of V or something like that. Is that the idea?
Z ends up becoming a function of entropy and enthalpy.
Oh, I see. But I think this is kind of another approach to what's usually people use van der Waals equation, right, which modifies the ideal gas law by taking into account the volume that's excluded from V by the other atoms, and what's the other one? Takes into account, I guess, the interactions between the atoms, right?
And if you go to plasma states, it starts to compress.
Well, okay. So PV equals Z nRT, right? Something which is just basically a way of taking the ideal gas law and preserving it by putting in a function which does the magic that's necessary to make it look like an ideal gas when it really isn't. It's kind of like a personal dome of vision, I think, for those who get the reference. Okay, everybody, I think we're done here. Thanks for coming, and let's see. Yeah, so until next week, when we continue the series, pretty sure.
Can we just revisit the thing about the coins?
About the coins?
Ordinary use of the coins, any pattern that appear in the sequence with equal frequency, right? Let's say any three flip pattern. There's no 3-flip pattern that would be preferred, right?
I would think you could say the same thing for any n member pattern, right?
Right, but if we indulge,
I would subject the pattern would change if it was made out of iron versus gold.
So, but now you're introducing a non-random element. You're some ferromagnetism or something, but I don't think that's where Benjamin is going.
If we're flipping coins, we get the same pattern, the same probability of every pattern, until we introduce some kind of if statement. So, for example, if I don't get my pattern, then I start over, is an if statement. So an if
Right.
statement is also a filter.
Is a what?
And the point is a filter, right? If is a filter because some
A
things go
filter.
through
Okay.
and some
Yeah.
things don't, right? In an if statement, by definition. So the point is that in order to get inhomogeneous results with a coin flipping, we need a filter, an if. But if we have a filter, we can get anything we want.
Oh, now I know where
Depends
you're
on the
going with
filter,
this.
right? Filtering is everything. That's what I mean, right? So if we allow filtering, then we're no longer coin flipping. That's all I'm saying.
Right. And what could you possibly be getting at with
Nothing at all.
that? Okay, good. All right. Well, thank you, Benjamin, for that. Thank
the
you
hardest
more than
people
you
to
know
educate-
for that.
The
Yeah.
hardest people to educate are the people that don't want to learn. So I have to do this very carefully.
Okay. So goodbye until next week. And as we leave, I will just leave you with this goodbye look.